Hello and welcome. My name is Alan and I have a stain on my shirt that I couldn't see normally, but it shows up there. Anyway, uh, pull your seat up, grab you something to drink. We're going to read more Einstein's Ideas and Opinions. We are reading a new piece today. It is called The Fundamentals of Theoretical Physics. Blurb reads from Science, Washington, D.C., May the 24th, 1940. Science is the attempt to make the chaotic diversity of our sense experience correspond to a logically uniform system of thought. In this system, single experiences must be correlated with the theoretic structure in such a way that the resulting coordination is unique and convincing. With the sense experiences are the given subject matter, but the theory that shall interpret them is man-made. It is the result of an extremely laborious process of adaptation. Hypothetical, uh, never completely final, always subject to question and doubt. The scientific way of learning concepts differs from that which we use in our daily life, not basically, but merely in the state. In the more precise definition of concepts and conclusions, more painstaking and systematic choice of experimental materials, and greater logical economy. By this last, we mean the effort to reduce all concepts and correlations to as few as possible logically independent basic concepts and axioms. What we call physics compromises the group of natural sciences which base their concepts on measurements, and whose concepts and propositions lend themselves to mathematical formulation. Its realms is accordingly defined as that part of the sum total of our knowledge which is capable of being expressed in mathematical terms. With the progress of science, the realm of physics has so expanded that it seems to be limited only by the limitations of the method itself. The larger part of physical research is devoted to the development of the various branches of physics, in each of which the object is the theoretical understanding of more or less restricted fields of experience, and in each of which the laws and concepts remain as closely as possible related to experience. It is this department of science, with its ever-growing specialization, which has revolutionized practical life in the last centuries and given birth to the possibility that man may at last be freed from the burden of physical toil. On the other hand, from the very beginning there has always been present the attempt to find a unifying theoretical basis for all the single sciences, consisting of a minimum of concepts and fundamental relationships from which all the concepts and relationships of the single disciplines might be derived by logical process. This is what we mean when we by the search for a foundation of the whole of physics. The confident belief for a uh, that the ultimate goal may be reached, is the chief source of the passionate devotion which has always animated the researcher. It is in this sense that the following observations are devoted to the foundations of physics. From what has been said, it is clear that the word foundations in the connection does not mean something analogous to, in all respects, to the foundations of a building. Logically considered, of course, the various single laws of physics rest upon this foundation. But whereas a building may be seriously damaged by a heavy storm or spring flood, yet its foundations remain intact. In science, the logical foundation is always in greater peril from new experiences or new knowledge than are the branch disciplines with their closer experimental concepts. In the connection of the foundation with all the single parts lies its great significance, but likewise its greatest danger in face of any new factor. When we realize this, we are led to wonder why the so-called revolutionary epochs of the science of physics have not more often and more completely changed its foundation than has actually been the case. The first attempts to lay a uniform theoretical foundation was the work of Newton. In his system, everything is reduced to the following concepts. 1. Mass points with invariable mass. 2. Action at a distance between any pair of mass points. 3. Law of motion for the mass point. There was not, strictly speaking, any all-embracing foundation because an explicit law was formulated only for the actions at a distance of gravitation, while the other actions at a distance, nothing was established a priori except the law of equality of actio and reactio. Moreover, Newton himself fully realized that time and space were essential elements as physically effective factors of his system, if only by implication. This Newtonian basis proved eminently fruitful and was regarded as final up to the end of the 19th century. It not only gave results for the movements of the heavenly bodies down to the most minute details, but also furnished a theory of the mechanics of discrete and continuous masses, a simple explanation of the principle of conservation of energy, and a complete and brilliant theory of heat. The explanation of the facts of electrodynamics within the Newtonian system was more forced, least convincing of all. From the very beginning was the theory of light. It is not surprising that Newton would not listen to a wave theory of light, for such a theory was most unsuited to his theoretical foundation. The assumption that space was filled with a medium consisting of material points that propagated light waves without exhibiting any other mechanical properties must have seemed to him quite artificial. The strongest empirical arguments for the wave uh, nature of light, fixed speeds of propagation, interference, diffraction, polarization were either unknown or else not known in any well-ordered synthesis. He was justified in sticking to his corpuscular theory of light. During the 19th century, the dispute was settled in favor of the wave theory. Yet no serious doubt of the mechanical foundation of physics arose. In the first place, because nobody knows where to find a foundation of another sort. Only slowly, under the irresistible pressure of facts, there developed a new foundation of physics, field physics. From Newton's time on, the theory of action at a distance was constantly found artificial. Efforts were not lacking to explain gravitation by kinetic theory, that is, on the basis of collision forces of hypothetical mass particles, but the attempts were superficial and bore no fruit. The strange part played by space or the inertial system within the mechanical foundation was so clearly recognized and criticized with especial clarity by Ernst Mach. The great change was brought about by Faraday, Maxwell, and Hertz. As a matter of fact, half unconsciously and against their will. All three of them, throughout their lives, considered themselves adherents of the mechanical theory. Hertz had found the simplest form of the equations of the electromagnetic field and declared that any theory leading to these equations were Maxwellian theory. Yet, toward the end of his short life, he wrote a paper in which he presented as a foundation of physics a mechanical theory freed from the force concept. For us, who took on Faraday's ideas, so to speak, with our mother's milk, it is hard to appreciate their greatness and audacity. Faraday must have grasped with unerring instinct and artificial nature of all attempts to refer electromagnetic phenomena to action at a distance between electric particles reacting on each other. How was each single iron filing among a lot scattered on a piece of paper to know of the single electric particles running around in a nearby conduction? All these electric particles together seem to create in the surrounding space a condition which in turn produced a certain order in the filings. The spatial states today, called fields, if their geometrical structure and independent action were once rightly grasped, would, he was convinced, furnish the clue to the mysterious electromagnetic interactions. He conceived these fields as states of mechanical stress in a space filling stadium similar to the states of stress in an elastically distended body. For at that time, this was the only way one could conceive of states that were apparently continuously distributed in space. The peculiar type of mechanical interpretation of these fields contained in the background a sort of placation of the scientific conscience in view of the mechanical tradition of Faraday's time. With the help of these new field concepts, Faraday succeeded in forming a qualitative concept of the whole complex of electromagnetic effects discovered by him and his predecessors. The precise formulation of the time-space laws on those fields was the work of Maxwell. Imagine his feelings when the differential equations he had formulated proved to him that the electromagnetic fields spread in the form of polarized waves and with the speed of light. To few men in the world has such an experience been vouched as fed. At the thrilling moment, um, he surely never guessed that the riddling nature of light, apparently so completely solved, would continue to baffle succeeding generations. Meantime, it took physicists some decades to grasp a full significance of Maxwell's discoveries. So bold was the leap that his genius forced upon the conceptions of his fellow workers. Only after Hertz had demonstrated experimentally the existence of Maxwell's electromagnetic waves did resistance to the new theory break down. But if the electromagnetic field could exist as a wave independent of the material source, then the electromagnetic interaction would no longer be explained as action at a distance, and what was true for electrical action could not be denied for gravitation. Everywhere Newton's actions at a distance gave way to fields spreading with finite velocity. Of Newton's foundation, there now remained only the material mass point subject to the law of motion. But J.J. Thomson pointed out that an electrically charged body in motion must, according to Maxwell's theory, possess a magnetic field whose energy acted precisely as does an increase of kinetic energy to the body. If then a part of the kinetic energy consists of field energy, might that not then be true of the whole of the field of the kinetic energy? Perhaps the basic property of matter, its inertia, could be explained within the field theory. The question led to a problem of an interpretation of matter in terms of field theory, the solution of which would furnish an explanation of the atomic structure of matter. It was soon realized that Maxwell's theory could not have accomplished such a program. Since then, many scientists have zealously sought to complete the field theory by some generalization that should comprise a theory of matter. But so far, such efforts have not been crowned with success. In order to construct the theory, it is not enough to have a clear conception of the goal. One must have a formal point of view which will sufficiently restrict the unlimited variety of possibilities. So far, this has not been found. Accordingly, the field theory has not succeeded in furnishing a foundation for the whole of physics. For several decades, most physicists clung to the conviction that a mechanical substructure would be found for Maxwell's theory, but the unsatisfactory results of their efforts led to gradual acceptance of new field theory concepts as irreducible fundamentals. In other words, physicists resigned themselves to giving up the idea of a mechanical foundation. Thus, physicists held to a field theory program, but it could not be called a foundation since nobody could tell whether a consistent field theory could ever explain, on the one hand, gravitation, on the other hand, the elementary components of matter. In this state of affairs, it was necessary to think of material particles as mass points subject to Newton's laws of motion. This was the procedure of Lorentz in creating his electron theory and the theory of electromagnetic phenomena of moving bodies. Such was the point at which fundamental conceptions had arrived at the turn of the century. Immense progress was made in the theoretical penetration and understanding of whole groups of new phenomena, but the establishment of a unified foundation for physics seemed remote indeed. And this state of things has even been aggravated by subsequent developments. For development during the present century is characterized by two theoretical systems essentially independent of each other: the theory of relativity and the quantum theory. The two systems do not directly contradict each other, but they seem little adapted to fusion into one unified theory. We must briefly discuss the basic idea of these two systems. The theory of relativity arose out of the efforts to improve, with reference to logical economy, the foundation of physics as it existed at the turn of the century. The so-called special or restricted relativity theory is based on the fact that Maxwell's equations, and thus the law of propagation of light is in empty space, are converted into the equations of the same form when they undergo Lorentz's transformation. This formal property of the Maxwell equations is supplemented by our fairly secure empirical knowledge that the laws of physics are the same with respect to all inertial systems. This leads to the result that the Lorentz transformation applied to space and time coordinates must govern the transition from one inertial system to any other. The content of the restricted relativity theory can accordingly be summarized in one sentence: all natural laws must be so conditioned that they are covariant with respect to Lorentz's transformations. From this, it follows that the simultaneity of two distant events is not an invariant concept, and that the dimensions of rigid bodies and the speed of clocks depend upon the state of motion. A further consequence was a speed of a given body was not small compared with the speed of light, which followed also the principle of the equivalence of mass and energy, with the laws of conservation of mass and energy becoming one and the same. Once it was shown that simultaneity was relative and depended on the frame of reference, every possibility of retaining actions at a distance within the foundation of physics disappeared, since that concept presupposed the absolute character of simultaneity. It must be possible to state the location of the two interacting mass points at the same time. The general theory of relativity owes its origin to the attempts to explain a fact known since Galileo's and Newton's time, but hitherto eluding all theoretical interpretations. The inertia and the weight of a body in themselves, two entirely distinct things, are measured by one and the same constant, the mass. From this correspondence follows that it is impossible to discover by experiment whether a given system of coordinates is accelerated or whether its motion is straight and uniform, and the observed effects are due to a gravitational field. This is the equivalence principle of the general theory of relativity. It shatters the concepts of the inertial system as soon as the gravitation enters in. It may be remarked here that the inertial system is a weak point of the Galilean Newtonian mechanics, nor there is presupposed a mysterious property of physical space, conditioning the kind of coordinate systems for which the law of inertia and the Newtonian law of motion hold good. These difficulties can be avoided by the following postulate. Natural laws are to be formulated in such a way that their form is identical for coordinate systems and any kind of states of motion. To accomplish this is the task of the general theory of relativity. On the other hand, we deduce from the restricted theory the existence of a Riemannian metric within the time-space continuum, which, according to the equivalence principle, describes both the gravitational field and the metric properties of space. Assuming that the field equations of gravitation are of a second differential order, the field law is clearly determined. Aside from the results, the theory frees field physics with the disability it suffered from, in common with the Newtonian mechanics, of ascribing to space those independent physical properties which heretofore had been concealed by the use of an inertial system, but it cannot be claimed that those points of the general relativity theory which can today be regarded as final have furnished physics with a complete and satisfactory foundation. In the first place, the total field appears in it to be composed of two logically unconnected parts, the gravitational and the electromagnetic. And in the second place, this theory, like the earlier field theories, has not up until now supplied an explanation of the atomistic structure of matter. This failure has probably some connection with the fact that so far it has contributed nothing to the understanding of quantum phenomena. To take in these phenomena, physicists have been driven to the adoption of entirely new methods, the basic characteristics of which we shall now discuss. In the year 1900, in the course of purely theoretic investigation, Max Planck made a very remarkable discovery. The law of radiation of bodies as a function of temperature could not be derived slowly from the laws of Maxwellian electrodynamics. To arrive at results consistent with the relevant experiments, radiation of a given frequency had to be treated as though it consisted of energy atoms of the individual energy HV, where H is Planck's universal constant. During the years following, it is shown that light was everywhere produced and absorbed in such energy quanta. In particular, Niels Bohr was able largely to understand the structure of the atom on the assumption that atoms can only have um, discrete energy values, and that the discontinuous transitions between them are connected with the emission or absorption of such an energy quantum. This threw some light on the fact that their gaseous state elements and their compounds radiate and absorb only light of certain sharply defined frequencies. All this was quite inexplicable within the frame of the hitherto existing theories. It was clear that, at least in the field of atomistic phenomena, the character of everything that happens is determined by discrete states and by apparently discontinuous transitions between them, Planck's constant H playing a decisive role. The next step was taken by de Broglie. He asked himself how the discrete states could be understood by the aid of the current concepts and hit on a parallel with stationary waves, as for instance in the case of the proper frequencies of organ pipes and strings in acoustics. True, wave actions of the kind are required were unknown, but they could be constructed and their mathematical laws formulated employing Planck's constant H. De Broglie conceived an electron revolving about the atomic nucleus as being connected with such a hypothetical wave train, and made intelligible to some extent the discrete character of Bohr's permitted paths of the stationary character of the corresponding waves. Now, in mechanics, the motion of material points determined by the forces of fields of force acting upon them. Hence, it was to be expected that those fields of force would also influence de Broglie's wave fields in an analogous way. Erwin Schrödinger showed how this influence was to be taken into account, reinterpreting by an ingenious method certain formulations of classical mechanics. He even succeeded in expanding the wave mechanical theory to a point where, without the introduction of any additional hypotheses, it became applicable to any mechanical system consisting of an arbitrary number of mass points. that is to say, possessing an arbitrary number of degrees of freedom. This was possible because a mechanical system consisting of these mass points is mathematically equivalent to a considerable degree to one single mass point moving in a space of 3n dimensions. On the basis of the theory, there was obtained a surprisingly good representation of an immense variety of facts which otherwise appeared entirely incomprehensible. But on one point, curiously enough, there was failure. It proved impossible to associate with these Schrodinger waves definite motions of the mass points, and that, after all, had been the original purpose of the whole construction. The difficulty appeared insurmountable until it was overcome by Born in a way similar to the as simple as it was unexpected. The de Broglie Schrodinger wave fields were not to be interpreted as a mathematical description of how an event actually takes place in time and space, though, of course, they have reference to such an event. Rather, they have a mathematical description of what we can actually know about the system. They serve only to make statistical statements and predictions of the results of all measurements which can carry out upon the system. Let me illustrate these general features of quantum mechanics by means of a simple example. We shall consider a mass point kept inside a restricted region G by forces of finite strength. If the kinetic energy of the mass point is below a certain limit, when the mass point, according to classical mechanics, can never leave then the mass point, according to classical mechanics, can never leave the region G. But according to quantum mechanics, the mass point, after a period not immediately predictable, is able to leave the region G in an unpredictable direction and escape into the surrounding space. This case, according to Gamow, is a simplified model of radioactive disintegration. The quantum theoretical treatment of this case is as follows at the time t to the subscript 0. We have a Schrodinger wave system entirely inside G. But from the time t subscript 0 onwards, the wave leaves the interior of G in all directions in such a way that the amplitude of the outgoing wave is small compared to the initial amplitude of the wave system inside G. The further these outside waves spread, the more the amplitude of the waves inside G diminishes. And correspondingly, the intensity of the later waves issuing from G. Only after infinite time has passed is the wave supply inside G exhausted, while the outside wave has spread over an ever-increasing space. But what has this wave process to do with the object of our interest, the particle originally enclosed in G. To answer this question, we must imagine some arrangement which will permit us to carry out the measurements on the particle. For instance, let us imagine somewhere in the surrounding space a screen so made that the particle sticks to it in coming into contact with it. Then the intensity of the waves hitting the screen at some point, we draw conclusions as to the uh, probability of the particle hitting the screen there at that time. As soon as the particle has hit any particular point of the screen, the whole wave field loses all its physical meaning. It's only the whole wave fit, or sorry, it's only the purpose it was to make the probability predictions as to the place and time of the particle hitting the screen, or, for instance, its momentum at the time when it hits the screen. All other cases are analogous. The aim of the theory is to determine the probability of the results of measurement upon a system at a given time. On the other hand, it makes no attempt to give a mathematical representation of what is actually present or goes on in space and time. And on this point, the quantum theory of today differs fundamentally from all previous theories of physics, mechanistic as well as field theories. Instead of a model description of actual space-time events, it gives the probability distributions for possible measurements as functions of time. It must be admitted that the new theoretical conception owes its origin not to any flight of fancy, but to the compelling force of the facts of experience. All attempts to represent the particle and wave features displayed in the phenomena of light and matter by direct recourse of a space-time model have so far ended in failure. And Heisenberg has convincingly shown from an empirical point of view that any decision as to a rigorously deterministic structure of nature is definitely ruled out because of the atomistic structure of our experimental apparatus. Thus, it is probably out of the question that any future knowledge can compel physics again to relinquish our present statistical theoretical foundation in favor of a deterministic one which would lead directly with physical reality. Logically, the problem seems to offer two possibilities between which we are in principle given a choice. In the end, the choice will be made according to which kind of description yields the formulation of the simplest foundation, logically speaking. At the present, we are quite without any deterministic theory directly describing the events themselves in the consonance with the facts. For the time being, we have to admit that we do not possess our general theoretical basis of physics, which can be regarded as its logical foundation. The field theory so far has failed in the molecular sphere. It is agreed on all hands that the only principle which could serve as the basis of quantum theory would be one that constituted a translation of the field theory into the scheme of quantum statistics. Whether this will actually come about in a satisfactory manner, nobody can venture to say. Some physicists, among them myself, cannot believe that we must abandon, actually and forever, the idea to direct representation of physical reality in space and time, or that we must accept the view that events in nature are analogous to a game of chance. It is open to every man to choose the direction of his striving, and to every man may draw comfort in Lessing's fine saying that the search for truth is more precious than its possession. Whew! Yeah, that was a long one. But Einstein talking about physics and how science can never be truly um, finished because it must also be able to be questioned and discussed by other matters and implications. And thus, how, the examples of field theory superseded Newtonian mechanics in parts of physics. But yeah, that'll be it for this episode. As always, educate thyself, think, read, study, learn. Someone tries to tell you something you have trouble believing, ask them to cite their sources. I'll see you all in the next episode. Until then, later.